The title of the lecture is The Role of the Civil Engineer in an Increasingly Automated Infrastructure World. And the aim of the presentation is really to describe why I feel civil engineers are best positioned to be the de facto thought leaders of automated infrastructure services going forward in this 21st century. Towards that end, the presentation is broken into 4 parts. I'd like to begin with a little bit of a historical perspective. Before we can talk about the role that civil engineers may play in the future, it's important to take note of what is our professional identity and why does that identity matter with respect to thought leadership in automated infrastructure. In the second part of the presentation, I'd like to highlight some of the technologies that are introducing opportunities for us professionally to take leadership of this exciting and high-value space. In the third part of the talk, I'd like to highlight some of the automated infrastructure research projects that we've undertaken at the University of Michigan to help prototype some of these solutions before they're deployed full-scale in operational infrastructure. And then finally, I'll wrap up with a few words of conclusion before opening the floor to the audience for questions. So let me begin with the historical perspective. Before describing the role of the civil engineer in automated infrastructure, the first question I would like to ask is, what exactly is a civil engineer? I think we can all agree that civil engineers are designers, constructors, and maintainers of the structures and systems that truly advance the common good of our society. We provide essentially the quality of life of our modern societies. We're also stewards of the environment and more recently, stewards of the global climate. If we look at our human habitats across the globe, we'll see the handiwork of civil engineers almost everywhere throughout the built environment, including marvels such as bridges and large-scale buildings, to the lifeline systems and transportation networks that are essential to the operation of our cities and our communities. Now, the notion of the civil engineer really finds its historical origins in continental Europe in the mid-1700s in the Kingdom of France. During that time period in the history of France, there was a rapid expansion of the national economy, requiring the king to install and invest heavily in transportation assets throughout the kingdom, including rising investments from 1726 all the way to the eve of the French Revolution in 1789, going from 2 million liveries to 25, constructing essentially new masonry bridges, paved roads, among others. But it's really not until 1747 that we see the establishment of the first school that's designed to train individuals to be civil engineers, specifically engineers in the pursuit of transportation assets, with the establishment of the National School for Bridges and Roads. In the second half of the 18th century, we see the momentum shift to Great Britain, where we see the first self-described civil engineer, John Smeaton, who established in 1771 the Smeaton Society of Civil Engineers. That momentum continued into the early 1800s with the establishment of the Institution of Civil Engineers, which was formed in 1818 as the first professional engineering society and actually the first global professional engineering society, with many countries then following the leadership of the ICE. The ICE really grew under the leadership of Thomas Telford through the 1820s. Now, if we look at the impact that civil engineers have had over the history of all of our nations, we'll see tremendous economic impact in much of our work. In the case of my own home country, the United States, we see the establishment of transportation networks that were critical to the maturing and the opening of our national economy, beginning with the establishment of the Erie Canal, a 300-plus mile canal connecting New York City and the eastern seaboard to the frontier areas of the Great Lakes. Later in the second half of the 1800s, we see the first transcontinental railroad connecting our east and our west coast and really fueling westward expansion of the country, all the way to our post-World War II period, where we saw heavy investment in our transportation networks in the form of the Interstate Highway System, which was established by an act of Congress in 1956. That interstate system transformed the economy, allowing all of our supply chains and our national industries to essentially be national, connecting goods, people with markets. We see that even in the modern era. We see the establishment, for example, of investments in grids in Germany, leading to rapid adoption of renewable energies such as onshore and offshore wind, as well as solar power, where today those investments in grid have translated into 56% of the German energy portfolio being from renewables. We also see more recently in 2013 the establishment of the China Belt and Road Initiative, which is largely an infrastructure initiative designed to connect the Chinese market with the larger global economy. Now, before talking about some of the technological opportunities of the profession, I would like to highlight that one of the key attributes of our profession is that we truly do advance the common good. We view infrastructure as a public resource for the common good, where our profession has always been the one that protects the safety of our public in the use of the infrastructure systems. We're also responsible for ensuring that the design and the construction of those infrastructure systems are sustainable. And furthermore, we're also required by our code of ethics to be inclusive and to solicit the perspective community. These professional attributes that codify us as the leaders of the common good really are embodied in the code of ethics that many of our professional societies, including the American Society of Civil Engineers, have. This code of ethics in the United States dates back to 1914, from ASCE establishing a code of ethics committee with Rear Admiral Mordecai Endicott in leadership, and this code of ethics continues today. Now, today is one of the best times probably in the history of civil engineering to be a civil engineer. Where is our leadership needed? We see it in rapid population growth throughout the world and rapid urbanization, essentially the densification of populations within large cities, including megacities, which are defined as cities having 10 million or more inhabitants. This concentration of population obviously puts heavy demand on our infrastructure systems. We're also going to, if we extrapolate current trends of urbanization forward, we're going to have to accommodate another 2 to 2.5 billion people in cities by 2050. A big challenge for accommodating that growth is how do we do it without adding carbon to our atmosphere? That leads us to the second grand challenge that civil engineers have an opportunity to play a leadership role in, and that's climate change. Climate change is really the result of the 20th century's use of fossil fuels, which now we're starting to see the impacts of with onset events from climate change, including desertification, ocean acidification, rain pattern shifts that have led to water scarcity issues and tremendous storm events throughout our world. We're already seeing global warming, where certain parts of the globe warming more rapidly than others, including the North Pole, where we see on an average a 3-degree centigrade increase, leading to an acceleration of ice melt on the North Pole. We're seeing this non-stationarity demand our profession to begin to think about adaptation strategies for our habitats, particularly those that are on our coastlines that are subject to growing sea levels, thinking through ways to add resilience to many of our coastal habitats. We also need leadership in innovation that's going to be associated with how we're going to accommodate urban growth without emitting more carbon dioxide to our atmosphere. We're also likely to play a role in negative emission technologies that will begin to essentially remove carbon from our atmosphere. Another area where leadership is needed is the financial burden of our infrastructure, which continues to grow. Many developed nations are contending with aging infrastructure stock, and deferring investment can only lead to catastrophic failure of our infrastructure, such as we've seen in the United States. An example shown here is the San Bruno pipeline explosion in 2010, undetected corrosion to aged buried pressurized gas pipelines. There's also questions around the role of public investment. Currently, public investment, particularly in North America, remains a dominant investment model for funding our infrastructure, but does that remain the best approach? If we were to introduce more private investment in our infrastructure, does that ensure equitable access to the benefits that our infrastructure design provide? And there's many examples that we see across North America of privatization of infrastructure services associated with private financing behind infrastructure projects. Now, a question must be asked, given these grand challenges, are we positioned as a profession to lead? One of the challenges that we see going forward is a global commoditization of the profession, leading to tighter profit margins, which adds challenges associated with finding qualified candidates and retaining those candidates within our organizations. Now, while market consolidation of the industry is helping with efficiencies and talent access, one of the challenges we see is a lack of funding in new technologies across the industry. For example, a recent study done by Deltek Clarity, which studies essentially 4,000 North American engineering consulting firms nationally, finds that when asked, do engineering firms see value in some of these emerging technologies area? And surprisingly, many of the emerging technology areas that are going to be critical to the future of our profession are deemed as not important for investment. Does that set us up for success as we think about increasing automation of our infrastructure? There's also a growing concern about our talent pipeline, particularly in the United States. Shown here is just enrollments in bachelor's of engineering programs across the United States in civil and environmental engineering. And you'll see over the past 7 years, we've had a steady decline from 15% of all bachelor's of engineering degrees in the United States to only 10%. That essentially is a challenge associated with recruiting the best and the brightest into our profession. We're going to need that talent to be leaders in this automated infrastructure world for certain. So let me talk a little bit about the technologies that are emerging in the field and the opportunities that they present for us professionally. One of the first amazing technologies of the 20th century is the miniaturization of sensors, making sensors both miniature as well as low cost. Some of the key technology drivers there that have really driven a new era of sensing technologies is microelectrical mechanical systems, or MEMS sensors. We see many of these sensors throughout many forms of life, including our cell phones, all the way to infrastructure systems. These technologies essentially have put into reach high density of sensing that we're now beginning to see throughout the built environment. Another key technology development is computing power, which has continued to increase under Moore's law. Initially, it was based on densification of transistors on a microprocessor, but today that trend continues through the introduction of parallelization within the design of our computational cores. We've also seen an explosion in communication technologies, both in the form of Edholm's law, which is looking at the rapid rate of communication bandwidth that's associated with wireless communication technologies, where we're seeing convergence of wireless and wireline bandwidths converging by the mid-2030s. Also the internet, which is really a massive global scale communication system that allows for the communication between people as well as between devices. Finally, machine learning has emerged as a very powerful analytical approach for contending with the amount of data that we may be collecting from a sensed world. First instances of machine learning really find themselves in the field of pattern classification, which is an applied mathematics study of statistical analysis of data to automate the assignment of data to inherent classes, allowing us to classify our world in autonomous ways. That's matured into artificial intelligence and machine learning, which builds off of pattern classification to provide automated algorithms that improve the performance through learning, essentially learning from data. And there's many examples of that, ranging from artificial neural networks to deep learning convoluted neural networks. Now, civil engineering as a profession has always been a technology leader in the adoption of sensing and actuation technologies to automate our infrastructure systems. We see examples of sensors in the form of monitoring systems and actuators in the form of control systems in many civil engineering structures, ranging from marquee structures in areas where natural hazards are concerned, such as our long-span bridges on the west coast of the United States, where we see permanent seismic monitoring systems, to proactive control systems that can control undesired deflection and motion of structures during seismic and large wind events, such as structures throughout the seismic areas of Asia. And you can see examples here from Tokyo of Mori Tower, which has 350 semi-active hydraulic dampers trying to control that structure during moderate strong ground motion and typhoon winds. But today we're seeing a shift away from the traditional interpretation of data that we may collect in our sensing and our actuation systems that have historically been based on partial differential equation type analysis to ones that are based on data-driven methods through the invocation of scalable computing power that's available through the cloud. So communication has made computing on demand available to many of our sensing and control systems, transforming what we can do with data and how that data can enhance the performance of our monitoring and our control systems. This dramatic shift essentially has created a new class of intelligent infrastructure that's often referred to as a cyber-physical system, where the distinguishing characteristic of a cyber-physical system from more traditional intelligent infrastructure is the use of computing power and essentially data-driven analytics to process data we may collect. And there's many examples of these CPS systems throughout our infrastructure systems, including early earthquake warning systems, connected autonomous vehicles, and even the way we inspect our infrastructure through the use of drones and unmanned aerial vehicles that give us access to structures we did not have before. Now, the importance of automation cannot be underscored. And CPS frameworks are essential for providing solutions for many of the grand challenges problems that I framed at the beginning of the presentation. For example, automation is going to be key in our arsenal of solutions that will be necessary for battling climate change. For example, sensing and actuation may be critical to developing adaptive infrastructure systems that truly add resilience to many of our coastal communities. Data-driven assessment based on data collected from CPS systems embedded in our infrastructure will be important in terms of helping us manage aging infrastructure in a risk-informed manner. Urbanization, we can unlock capacity of many of our built infrastructure systems by enhancing them with cyber-physical system capabilities. We also can increase professional valuation in our talent pipeline by really putting automation front and center as a core competency of our profession. But a question must be asked, given the opportunity that these technologies, particularly automation, can play in addressing many of the grand challenge areas that we're being asked to lead, are we truly in a position of leadership? Let us consider, for example, the area of transportation. Historically, civil engineering has been the designers and the managers of our transportation assets and systems. This can include our infrastructure assets like bridges and roads, to our signal technologies, all the way to the design and the management of our transportation systems, where we look at traffic flow and econometrics. However, in the past 5 years, we're seeing a rapid emergence of what's often referred to as mobility service providers now coming directly into the transportation space. And this represents a form of service that is built on top of our infrastructure, now viewing infrastructure essentially as the operating system, but these infrastructure services being the applications built on top. Now, these services, including on-demand rideshare, mapping technologies, as well as the collection of data to understand social systems, are generally proven to have higher market valuations than the commodity markets of designing our road assets. So as a profession, we can essentially be more strategic about capturing higher valuation by being the leaders of the infrastructure service space. But one of the challenges we see in infrastructure services is that this particular space is largely being led by individuals with expertise outside of civil engineering. If we look at just the array of smart city startups that are emerging globally, we'll see that there's been heavy investments, trillions of dollars nationally, from venture capital firms investing in fundamentally infrastructure applications through the form of infrastructure services, ranging from parking to disaster management to transportation. While these particular businesses have high valuations, they often do not have strong civil engineering leadership at the helm of many of these solution providers. So where do we fit going forward? So today, infrastructure services are largely being led by the IT sector. They're offering solutions and collecting data and using that data and monetizing that data with approaches that often lack transparency. They're also being essentially utilized, the data that's being collected by many of these infrastructure services, leading to new forms of private financing for infrastructure projects. And we see that as a dominant financing approach in the smart city space today. So civil engineering leadership is needed in this space. We need to recognize professionally that it is our domain expertise that's going to extract a true value from the data that's being collected by many of these infrastructure services today. Not only that, we're uniquely positioned as the engineering profession that really looks at commonwealth generation over personal wealth, meaning that we have a role to play to ensuring equitable access to many of these infrastructure services, particularly as we see increasing roles of private financing in this space. So civil engineers must play a lead role in future infrastructure automation solutions by positioning the profession to offer high-value infrastructure service solutions in addition to our traditional offerings of essentially designing, constructing, and managing infrastructure assets. So in my department at the University of Michigan, the Department of Civil and Environmental Engineering, we've been grappling with many of these issues as an academic community for a number of years, and have recently published a new strategic vision for our department defining what the future role of civil engineers may be in this 21st century. And we defined 5 strategic directions that we truly believe will define our profession going forward. We feel there's opportunity for us to enhance the experiences of people within our habitats, introducing concepts of social science and public health directly into our portfolio of work. Also leading in adaptation. While we can hope for mitigation climate change, I think we have to prepare for that and adapt our habitats to be resilient against climate change. In order to battle climate change, we have to be thoughtful and innovators in how we shape our resource flows. And we have to leverage new tools and technologies, including automation and smart infrastructure financing, to essentially accelerate the adoption of technologies. So the remainder of my talk today will highlight some of the work we're doing in one of these strategic areas, our automation strategic area, here at the University of Michigan. So the first application I'd like to highlight is an application that I myself have been involved in, which is looking at the deployment of cyber-physical systems within highway corridors to aggregate data that had not previously been aggregated before, namely data from our infrastructure assets, as well as from the flow, the traffic flows that we see on those assets. And I'd like to acknowledge collaborators on this work being Kinsho Law, Professor of Civil and Environmental Engineering at Stanford, and Dr. Mohamed Etune, Principal Emeritus at Thornton Tomasetti, formerly Weidlinger Associates, for this work. We've been designing a cyber-physical systems that have been deployed on an operational highway corridor here in the state of Michigan, known as the Interstate 275 corridor, which is a 20-mile corridor from the Michigan-Ohio border at Toledo all the way up to the Detroit metropolitan area. We've instrumented a number of bridges along this particular corridor with permanent wireless structural health monitoring systems. And two of the bridges that I'll highlight today is the Telegraph Road Bridge and the Newburgh Road Bridge. But we've also integrated in that cyber-physical systems traffic cameras to understand traffic loads and weigh and motion stations to measure the loads on our infrastructure assets. The two bridges that are instrumented is the Telegraph Road Bridge and the Newburgh Road Bridge. These are 40-year-old bridges. They're very standard type steel deck girder bridges that are widely used in the United States. And it represents an opportunity for us to look at how to deploy in a cost-effective way structural health monitoring technologies and cyber-physical systems to manage what is here in North America a dominant bridge type within our national inventory of bridges. Both of these bridges have experienced some form of deterioration over their lifespan, but in particular, the Telegraph Road Bridge had its deck replaced in 2011 due to poor deck conditions, which is not uncommon in these parts of the United States where we have harsh winters and we widely use de-icing salts on our roads in those winter environments. We've deployed on both of these bridges permanent monitoring systems using a network of wireless sensor nodes that are called Narada sensor nodes. These sensor nodes were developed more than 15 years ago here at the University of Michigan, but have been deployed on more than 24 structures worldwide. You'll see here two examples of these monitoring systems. These are essentially solar-powered wireless sensor nodes that are going to be deployed on our bridges to collect data from a different variety of sensors ranging from strain gauges all the way to accelerometers and thermocouples. On the first bridge, the Telegraph Road Bridge, we have deployed 38 sensor nodes collecting over 70 channels, and we've been essentially collecting data from this bridge since 2011. So we're approaching nearly a decade of performance data that's been collected from this particular bridge nonstop. Also, the Newburgh Road Bridge has a lighter monitoring system on it with only 10 sensing channels collected by 5 sensing nodes, and this bridge has been monitored since 2017. And I'll highlight some of the data from these bridges shortly. In addition to monitoring the bridges, one of the aims of our cyber-physical system is really to understand what the imposed load is on these particular bridge structures so that we can correlate bridge responses and long-term deterioration with the actual physical vehicle loads that these bridges are seeing day in, day out. Towards that end, we have a weigh and motion system on that corridor. This is roughly 15 miles north of the Telegraph Road Bridge. So these weigh and motion stations are not co-located with the bridges, but nonetheless provide rich data on the trucks we're seeing in those corridors, including their speed, the number of axles, and the distribution of weights on their axles. In order to combine data from the weigh and motion station to the bridges that are further upstream, many miles away, we use computer vision, where we've deployed traffic cameras along the roadside of this corridor to essentially in real time track traffic and then use embedded deep learned detectors to detect trucks and truck events and use our cyber-physical system to communicate those truck events throughout that system, thereby triggering the data collection activities of the cyber-physical system. Now, in the first few years of deployment of these bridge monitoring systems, we largely collected data from these solar-powered sensors on a schedule-based process. So from 2011 to 2016, we scheduled data collection every 4 hours for a few minutes. If we saw traffic loads on the structure, then we collected the response. But if there was no traffic load, then we would not see measurable behavior of those structures, but we would collect that data. This was necessary to optimize the performance of the monitoring system, which is a solar-powered system. So we do not have unlimited energy, but we need to be very strategic in the deployment of that energy. Now, the aim, though, is not to just collect data from the response of those bridges, but we're more specifically interested in the response of those bridges to heavy truck loads, which are the known loads to deteriorate those structures. So we use a cyber-physical system and the communication across the internet between our cameras, our bridge monitoring systems, and our weigh in motion station to essentially automate the detection of trucks and then to trigger data collection based on the truck events we see moving in the corridor. In doing so, we can, for the first time, link the actual measured truck load measured at the WIM station with the bridge responses we see down at the bridges and begin to look at correlated relationships between bridge behavior due to the same set of truck loads. In order to do that, we have embedded a number of off-the-shelf computer vision algorithms that are based on deep learning methods. Namely, we have a single-stage detector that's based on a convoluted neural network architecture. It's often referred to as YOLO, which was introduced by Redmond et al. In 2015. It's a very high-speed detector that, once trained, gives us high levels of accuracy and precision in the detection of trucks. We have a tiny version of this embedded directly in a GPU that sits roadside with our cameras, allowing us to, once trained, to essentially automate the detection of trucks in real time at the detection rate that's equivalent to the frame rate of our cameras, which is at roughly 10 Hertz. We also then have to perform re-identification. It's one thing to detect trucks at each of the camera locations, but we need to then be able to say that the truck we see at one bridge is the same truck we see at the other bridge or at the weigh-in-motion station. So there we're using triplet networks to solve the re-identification problem, again built on YOLO version 3 Tiny, that essentially looks at using YOLO version 3 as an embedding network and looking at loss functions that are based on whether an image or a detected object is the same object seen in other images fed into that detecting network. Now, the result of that is that we have a cyber-physical system that can automate the tracking of heavy trucks, as you'll see here in these animations, where we can detect the truck once it comes onto the I-275 corridor and essentially alert our bridge monitoring systems to capture those events, and then finally see that truck event at the weigh-in-motion station. The end result is that we have one of the first ever data sets that actually has a measure of the truck load, essentially the gross vehicle weight and the axial weights distributed on the axle spacings that have been measured by our weigh-in-motion station, allowing us now to explicitly link the measurement of the truck load to the measured bridge responses we see within the corridor. One of the applications that we've been exploring with the use of the data is looking at relationships in the response of our structures to the population of truckloads. So these scatter plots correspond to essentially the peak responses at the different bridges against the gross vehicle weight, depending on the lane assignment of the truck, and looking at the correlation of peak responses at the two bridges, the Telegraph Road Bridge and the Newburgh Road Bridge here, using these as baseline models to establish normal, healthy behavior of these particular bridges, and trying to use these correlated relationships to look at anomalous behavior of deteriorated bridges within a population of measured bridges in the cyber-physical system framework. Now, one of the applications that we've applied that cyber-physical system to in partnership with our partner, the Michigan Department of Transportation, is using these long-term monitoring data sets to answer the question of durability of the structure. So instead of thinking of the application as a structural health monitoring problem, is thinking of it more as a structural durability monitoring problem, looking at the durability of the decks. In the Telegraph Road Bridge, that bridge has a long history of deck deterioration, as you'll see here, on both its wingspans as well as on its main span. A key attribute of this bridge is that it essentially has a main span that's supported by hanger plates using a pin and hanger connection off of these two wingspans that are on the north and south ends of the bridge. What we've observed before deck replacement in 2011 was that the center span, which is in full composite action, has almost no deterioration of the deck, a deck in very good structural condition. But the wingspans having essentially spoiled areas and potholes that are associated with poor deck durability. A key functional attribute of those wingspans is that they do not use shear studs and are in non-composite action. So the long-term monitoring data that we've collected over the past 15 years have helped us model the behavior of this non-composite connection between the deck that's essentially in a chemical bond interface with the steel girders beneath it. Part of our sensing strategy, knowing that one of our end goals was to essentially study the durability challenges that this bridge owner has seen on this bridge, is we've deployed essentially our sensors in an array that allows us to look at the flexural behavior of those bridge behaviors. So we have on those bridges essentially strain gauges through the height of the steel girders, as well as essentially a bridge diagnostic intelliducer, which is sort of like a full gauge strain gauge within the deck, that allows us to look at the flexural response of the structure under vehicle loading and look at the behavior specifically at the interface between the concrete deck and the steel girder, essentially looking at neutral axis location as well as slip strain as health metrics that can begin to describe the durability challenges of that bridge. Shown here is just some histograms associated with the estimated neutral axis that's associated with the data that we've collected over the past 15 years. And you'll see in the north and the south abutment spans where we're not in composite action that the neutral axis sits somewhere between being fully in composite action, which is the red line, to having no composite action, which is what the designer of that bridge would have assumed in the design of that steel, the steel rebar within that deck. In the center span where we are in composite action, we see essentially perfect neutral axis location associated with the behavior of the flexural response of that particular span under truck loads here, attesting to the integrity of the composite action that's intended through the introduction of shear studs on the steel girder at the concrete slab interface. What we've used the data for is to take the measurement of the gross vehicle weights that's exciting our structure and looking at the strain difference, or what we call slip strain, at the interface between the concrete deck and the steel girder in the non-composite area, to begin to model the nonlinear behavior of essentially partial composite action that exists based on chemical bonding and surface friction between the concrete slab and the steel girder. So long-term monitoring data has unraveled essentially empirically derived composite action models of partial composite action in these non-compositely designed steel girder slab spans. We've applied those models to a number of studies on the durability of those structures, looking at the implications of those nonlinear partial composite models on the durability of the deck, looking at the assumptions of the designer, which back in the early 1970s, based on AASHTO code, would have assumed no composite action, meaning that the negative moment area would have put larger degrees of essentially tensile strain on that deck due to partial composite action that we're observing based on our data. And that's allowed us to look at the durability of these particular wingspans. A second application of cyber-physical systems deployed in the civil infrastructure space are stormwater systems, essentially making them smart. And the work I'm about to present is that of my colleague, Professor Branko Kirkez here at the University of Michigan. Now, stormwater systems are critical infrastructure systems that are used essentially to collect rainwater during storm events and to bring it out to natural bodies of water. That's often done through the use of wastewater systems, where we have the challenge of combined sewer overflows due to very large storm events. For example, here in the Great Lakes region, this is a major issue for ensuring water quality of our Great Lakes. We have over 184 communities that have combined sewer overflow systems, where each year we see between 1,200 to 1,500 overflow events going out into the Great Lakes area. And this is essentially equivalent to upwards of 20 billion gallons of untreated wastewater that then spills out in the Great Lakes area. How do you solve this issue, particularly under the demands of climate change, is to essentially deploy great infrastructure solutions, which are very costly and take time to deploy. Now, one of the issues we're seeing in stormwater management is that due to climate change, we're seeing increasing frequency and intensity of storm events throughout many parts of our country. Here in the Great Lakes area, you'll see some examples from metropolitan Detroit. This is a flooding event that occurred around 2010 due to a very large summer storm event, leading to flooding of many roads and tunnel networks throughout the city of Detroit. This climate change requires us to react more quickly and more nimbly in solving a lot of these stormwater events with respect to the performance of our stormwater infrastructure. A solution is to utilize green infrastructure, which offers exciting possibilities to essentially provide a solution that's much lower cost, but much more environmentally responsible. In addition, green infrastructure not only to essentially solving demand issues on our stormwater systems, it improves water quality by lowering sediment and essentially taking utilization of retention time within the natural environment before those water flows come out to larger natural bodies of waters like lakes and rivers. Also, green infrastructure is known to revitalize urban areas by increasing property valuations through a proximate effect for properties that are in close proximity to green infrastructure. And shown here is just an example of one green infrastructure solution which ties to our critical stormwater systems by essentially providing more natural settings for water retention. Now, most green infrastructure systems are passive approaches. You design it and it performs as designed. But the question is, can we greatly enhance the performance of green infrastructure through cyber-physical systems? So the work of Professor Kirkes is looking at the deployment of wireless sensors and actuators that are cloud connected to the internet that essentially can monitor in real time storm events, the flow of water within our urban and our natural settings, and then to process that data in real time to essentially formulate control solutions that can control the flow of that stormwater within our habitat areas, thereby greatly enhancing the performance of our green infrastructure systems. The concepts of this are quite simple. In traditional infrastructure systems that are used for stormwater management, you essentially would have a storm event which occurs spatially over a regional area of your community. This is going to passively feed into your stormwater system, which, if the storm event is large enough, will essentially exceed the capacity of that stormwater event, leading to floods and overflows into natural waters bodies of raw sewage. The idea is to introduce monitoring and controls with a cloud-based controller to essentially move the movement of water in time and space spatially so as to alleviate the demand on your gray infrastructure systems. Doing that essentially through control and monitoring through the use of green infrastructure whose performance has been greatly enhanced by these embedded controllers and sensors. Shown here is one of the sensor nodes that Professor Kirkes would deploy, similar to the nodes that I deploy with my group. These are solar-powered nodes that have cellular interfaces that communicate directly to the cloud through a cellular modem. He can interface different types of sensing modalities to this node, including measurement of rain levels, depth sensors in bodies of water, soil moisture sensors, as well as water quality sensors. He can also control valves and gates to essentially control the flow of water within these watersheds. Shown here is one deployed watershed that he's instrumented. He's instrumented about 5 watersheds, 4 of which are here in the state of Michigan. He's managing nearly over 500 sensor nodes across the state of Michigan. But here in Ann Arbor, he has a fully instrumented network that's essentially a catch basin to the Huron River, which constitutes over 6,600 acres of land, 49% of which is impervious. So it's an urban watershed, if you will, with over 651 subcatchments. He's deployed throughout this urban watershed here in Ann Arbor, both sensor nodes to measure rain levels as well as levels of water within natural bodies, both our rivers, reservoirs, as well as our ponds. And then he's also installed essentially valves that are fully actuated based on commands coming in from the cloud from his cyber-physical system to essentially control the flow of water within the watershed. Shown here is an example of one of these cloud-controlled valves that uses wireless telemetry to the cloud to be actuated. You'll see here is a retention pond in one area of the city that's used as part of a larger green infrastructure system. So this retention pond is about 2 miles upstream of a natural pond area or a wetland area that's integral to the operation of this urban watershed here in Ann Arbor. And he uses essentially this valve to control the retention time of water within this pond before it comes into the green infrastructure system. So the way this works is the water during a storm event flows through the impervious surfaces of the built areas of the city until it essentially comes in this pond area where he's actuating through an actuated valve flow down into a creek that feeds into the Mary Beth Doyle Park area, which essentially has a retention pond for treatment of the water and controlling the flow of the water before it moves on to the Huron River. Shown here is actually an example of the use of the catch basin that is actuated. You'll see here's the flow of that and then the release of that flow animated based on actuated commands on his cloud actuated valve. Shown here downstream in that wetland area is essentially, once that valve's been opened, is an increasing level within these retention areas of this green infrastructure in the Mary Beth Doyle Park area of the city. Now, the impact of this work is, before deploying this automated watershed for stormwater management, this system was required to handle 15 million gallons of storage, roughly at $22 per gallon. This is associated with the gray infrastructure with the management of stormwater here in the city, where you would have essentially a total load of 600 pounds per year of total phosphorus within that water. But after the introduction of his cyber-physical system solution to stormwater management, we see a 50% increase in the capacity of the system, where the system now is able to retain up to 22.5 million gallons and actually have sediment of over 800 pounds per year of total phosphorus within natural settings before going into essentially our natural bodies of water. This has been estimated in the state of Michigan, where Professor Kirkes is deploying these systems statewide, is saving the city over $1 million of infrastructure alone, just based on this one cloud-based actuated stormwater watershed solution. The third example, and the final example I'd like to highlight, is the work of Professor Gabor Rose, who's jointly appointed between civil and environmental engineering and mechanical engineering, and is looking at improving safety and energy efficiency within our transportation networks through connectivity. Now, connectivity within our transportation networks is rolling out across the entirety of the United States, and it's largely been driven by a desire to enhance the safety of our transportation networks. Connectivity is also seen as the first step toward autonomous vehicles. But it's increasingly recognized as car manufacturers grapple with the challenges of fully autonomous vehicles that infrastructure has a very large role to play in automating in a safe manner autonomous vehicles within our roads. What they're observing is that the machine learning algorithms that are associated with LiDAR and camera imagery that's intended to give full situational awareness of vehicles are not able to mature fast enough to a level to ensure safety on many of these autonomous vehicles, requiring a rethink of essentially the role infrastructure is going to play in supporting these autonomous vehicles to achieve those levels of safety that will be necessary for wide-scale market adoption of full autonomy in our transportation network. Towards that end, here at the University of Michigan, we have an academic industry partnership called MCity, which involves industry partners from both automotive companies, our Michigan Department of Transportation, as well as high-tech companies, essentially looking at the state-of-the-art in both connected vehicles as well as connected infrastructure that are necessary to realize fully autonomous transportation networks here in the United States. As part of our enterprise, we have a 32-acre test facility called the MCity Test Track, and you'll see a picture here, which over 16 acres provides an off-road test environment for the testing of connectivity and autonomous vehicle technologies through a variety of different settings and challenges that are necessary to resolve before these connected autonomous vehicles will hit our roads. Some of the work that Professor Rose is doing is looking at connectivity between vehicles and the infrastructure to provide full awareness of what vehicles are doing directly on our infrastructure systems. Through the adoption of onboard connected vehicle units, shown here is one version of that. It's called Dedicated Short-Range Communication, or 802.11p, which gives seamless connectivity between vehicles communicating with one another as well as to infrastructure. Now, one of the challenges with connected vehicles, and the reason why connectivity is a critical piece, is that there's many safety applications that are called non-line of sight safety applications. So one particular area that connectivity is actually playing a major role is in what's called collision avoidance systems, essentially detecting vehicles well before the driver can see those vehicles, alerting the driver to enhance the safety and the reactive actions that that driver will take to ensure the safety of the vehicle and the passengers in it. So he's been looking at connectivity that's based on enhancing safety applications on our roads. And you can see an example shown here where he can utilize connectivity to more gracefully slow down a vehicle before encountering a vehicle that's essentially in a road blind spot. And you can see a video of this with an autonomous vehicle that Professor Rose has developed in his lab, where it's detecting a parked or hidden vehicle on the road, seeing that before the driver sees it, and autonomously slowing that vehicle to ensure it does not rear end the parked vehicle. Now, one of the exciting aspects of connectivity in the deployments that we've been deploying here at the University of Michigan is that we can begin to unravel the behavior of humans within a connected autonomous transportation network. So some of the work that Professor Rose has been doing is looking at true human subject data associated with how humans drive vehicles and how they react to events on the road, as we try to model human behavior in modeling both fully autonomous vehicles as well as connected but not autonomous vehicles that may be on the road. So shown here is a platoon of vehicles that he deploys with connectivity to collect empirical data on the behavior of those drivers under different road conditions, both in time and space. And shown here is the braking of vehicles as you have a car slowing down ahead of you, how vehicles behind that car begin to react. So this is human subject data on how human subjects drive their vehicles. That's informing the classical car follower model. This is actually a very classical dynamic model that describes human behavior behind the wheel with respect to the spacing between two consecutive vehicles. So as the gap h between vehicles begins to close, human subjects would naturally begin to slow down or press the brakes on the vehicle. We can use the data we're collecting from our connected autonomous vehicles to inform empirically tuning factors that are associated with the behavior of these models, essentially looking at these weighting factors alpha and beta that's associated with the behavior of drivers as they try to deaccelerate the car based on closing distance between the vehicle and the associated relative velocities between those vehicles. So we use empirical data to inform essentially models that are going to begin to model the behavior of human subjects. This is critically important as we think about how human subjects, non-autonomous vehicles, are going to interact with autonomous vehicles. Autonomous vehicles have to be able to anticipate human behavior in non-autonomous vehicles, and that's what these models are informing. So we're empirically deriving these important model calibration characteristics, alpha, beta, and tau, the time delay or the reaction time of the driver, based on empirical data collected from connectivity that we have today. That's informing models that then can be used that if you have connectivity of human-driven cars, how that connectivity may actuate an autonomous car, car 0, based on non-autonomous vehicles 1, 2, and 3 that are ahead of it on the road network, based on estimated distances between these vehicles that we can collect from connectivity packets that are being beaconed by each of these connected vehicles. Shown here is one of the challenges of this. This is actually a video from Hyundai that's looking at first attempts at trying to avoid crashes using autonomous vehicles. So you'll see a truck here, quickly press on the brakes. The control technologies in these vehicles have the ability to ensure that that vehicle does not rear end the truck, but you'll see a very dramatic response of all those autonomous vehicles, which can be dangerous and is certainly not fuel efficient. So Professor Rose has been looking at implementing control algorithms that are based on those car follower models that are defining the behavior of drivers that are human driving cars ahead but have connectivity to inform an autonomous car, car 0, which you'll see here in a moment in the video, to more gracefully brake to avoid collision. The implications of this are both for enhancing safety and understanding human behavior within models, dynamical models that will be necessary to enhance the safety of autonomous cars. But it's also powerful because it provides a way to quantify fuel savings that are associated with autonomy in vehicles. This is particularly important in the connected vehicle space with respect to trucks. There's a lot of interest in the trucking space for autonomy to enhance the fuel efficiency of our on-road trucks that are used to move freights within our national and our global supply chains. So shown here on this table is actually the gains of work, or the work saved, which translates directly into energy, on a per weight basis of the vehicle when you consider connectivity between having no cars inform you ahead, which represents the baseline work model, to having up to 3 cars ahead information informing the autonomous vehicle, resulting in 7% energy saving of the autonomous vehicle itself, or 19% energy saving for the autonomous vehicle itself, but 7% of all the traffic that sits behind that particular vehicle. We've more recently begun to expand this particular connected autonomous vehicle work by connecting essentially trucks to our infrastructure. So we can utilize connectivity to understand how trucks are moving on our roads and interacting with our bridges that may be instrumented with monitoring systems. And we're doing work right now in informing understanding of how a truck may influence the behavior of one bridge to control the truck further downstream on how it may interact with another bridge to minimize the dynamic amplification impact that those trucks have on our infrastructure. And we're doing that with an instrumented truck that we have here at the University of Michigan. And we're deploying this on our I-275 corridor. In the remaining 10 minutes, I want to pull together the different cyber-physical system and autonomous infrastructure systems that I just highlighted, the connected corridors, the connected stormwater systems, and connected vehicles, to really frame it as an opportunity for new business for the civil engineering profession. And much of the thought leadership here at the university in this particular regard is being led by my colleague, Professor Peter Adrians, who's the director of our Center for Smart Infrastructure Financing. Now, private financing in the foreseeable future is going to be an essential asset for us to resolve financial gaps that we see across our infrastructure space here in the United States, as well as in Europe and other mature economies. If we look at public infrastructure and the finance gap here, as published by the American Society of Civil Engineers in 2017, you'll see particularly for publicly financed infrastructure like roads and bridges, schools, as well as portways and waterways, really intimidating financial gaps in terms of what the current funding levels is and what the funding needs of maintaining these infrastructure in good order are. This is problematic because we have essentially cities, states, and even the federal government with increasing public deficits. We see increase in public debt relative to our gross domestic product, putting us in a weaker position to invest in infrastructure. And we're also not only seeing that, but we're seeing the inability of the public sector to truly deliver efficient investment solutions to resolve some of these financing gaps we see here. This is going to challenge the ability to deliver resilient infrastructure as well as sustainable or net zero infrastructure in the future. However, there is historical precedence for private investment within our field. And I'd like to highlight two examples of private financing that were absolutely vital to getting projects off the ground. And these are two very pivotal and historic projects here in the United States. The first is the one that I mentioned at the beginning of the talk, the Erie Canal. The Erie Canal was an ambitious canal project that was established by Governor DeWitt Clinton, the governor of New York State, in 1817. He went to federal Congress to essentially get funding for it. Congress was unable to essentially pass any legislation. So the state actually established a state-backed bond. It's one of the first examples of bond financing to finance large-scale infrastructure projects in the continental North American area. It cost $7.1 million to essentially deploy in 1818 money, if you will. But they essentially raised that funding through a fixed rate bond, which was paid off by tolls that were established on the Erie Canal. So it collected over $121 million of tolls before that bond was retired fully in 1882. Another example is the Golden Gate Bridge. A lot of people think the Golden Gate Bridge was actually built based on federal funding during the Great Depression in 1930. It actually wasn't. It got almost no federal or state funds to actually construct the Golden Gate Bridge. It was funded by what was called the Golden Gate Bridge and Highway District, which was really 6 adjoining districts in the Bay Area that pulled together and established a $35 million bond in the private markets, using essentially homes, farms, and businesses within the districts as the bond collateral. So it's actually a form of private financing by the public to essentially establish the funds necessary to construct the Golden Gate Bridge. More recently, we're seeing increasing roles of Wall Street within infrastructure, largely because investing in infrastructure has degrees of being recession-proof that you do not see in more commodity-based businesses. One example of that's innovative is what's known as environmental impact bonds. It's a new type of bond structure that really is what's called a performance-based bond that looks at performance of infrastructure and payoffs being calibrated based on performance. Now, an example of an environmental impact bond, one of the first here in the United States, was a project that was undertaken by DC Water a few years ago, where essentially DC Water was looking at storm overflow events within the Rock Creek area of the Washington, D.C. Water District. Was interested in deploying green infrastructure and essentially adopted an environmental impact bond. So what they did was Goldman Sachs and Calvert Foundation raised a $25 million fund in 2016 that had a 30-year maturity date paying off at a fixed interest rate of 3.43%. But it had a performance that would be assessed 5 years into the bond, which will be assessed next year in 2021, looking at essentially the effectiveness of that green infrastructure solution. And then having a one-time $3 million payoff, much like a swap, if you will, between DC Water and the investor community that's invested in that bond vehicle. So if the performance of that green infrastructure is normal, then no contingent payment is due in 5 years. But if the runoff reduction is greater than anticipated, then DC Water will make an outcome payment to the investor community of $3 million. And vice versa, if the green infrastructure was a failure, then the investors take that risk, and the investors pay essentially DC Water $3 million that can be reinvested to look at essentially combined sewer overflow issues within that catch basin. This is an exciting opportunity for our field because consulting engineers are essentially going to be the auditors of performance, much like you'll have essentially accounting firms serving as auditors of traditional investment vehicles. There's a role for civil engineers to be auditors of these performance-based financing vehicles. Now, towards that end, with investment proliferating across the smart city space, we really think there's a tremendous opportunity for civil engineering to come in and be a leader in forming the appropriate way to explore these new financing mechanisms that can be used to essentially drive applications of autonomy within our infrastructure systems and deploy infrastructure services. So we have the opportunity to unlock the value of data. We have the ability to provide unique insights to that data. And that allows the data actually itself to become a valuable asset of the infrastructure space. Not only is the physical asset valuable, but now the data it generates is equally valuable, if not more valuable, providing new business opportunities and new revenue streams for our profession. Also, we are essentially the ones that will be able to navigate how private financing can be deployed in a manner that's consistent with advancing the common good and ensuring equitable access to all benefits of privately financed smart city infrastructure. Now, when we think about infrastructure, we have to think about the role data is going to play on returns in some of these novel smart infrastructure financing instruments. And there's many precedents for that in our infrastructure space. Our road and our social infrastructure is often based on low risk but low return type fixed income investing, such as bonds. We have brownfield infrastructure that's more based on regulated infrastructure or utility grade infrastructure, much like our energy utilities as well as our ports and our airports, essentially having higher returns but higher levels of risk associated with the operational efficiencies of those infrastructure. But debt and private equity are essentially emerging in the brownfield infrastructure as well as in the greenfield infrastructure, much like the DC Water example I provided before. Now, smart infrastructure squarely fits within this risk-reward framework where we can see that there may be associated risk with the performance of our smart infrastructure, at least in the short term, but opportunity for the private finance community to derive higher levels of return associated with the performance of the infrastructure and our ability to monetize the data that we're collecting from our smart infrastructure. So the question is about data and the role data is going to play as we think about financing infrastructure going forward. So that can be data that's used to enhance operational efficiency, looking at instruments like environmental impact bonds or other type of performance-based bonds. Data can also be used to essentially have co-benefit valuations, looking at benefits that go beyond the benefit of the owner and using financing to rectify benefits that are derived more widespread benefits by different stakeholders in our society. And then also derivative cash flows that can be derived directly from our infrastructure and the assembly of different but synergistic data sets across a digitized built environment. Providing opportunities for new insurance and swap vehicles that can bring new financing directly into our infrastructure space. So just a few parting remarks. It's an absolutely exciting time to be in the field of civil engineering. The world needs us more than ever, while the technology that we have at our disposal is as empowering and exciting as ever before. And it's going to allow us to solve these large, grand challenges with the common good in mind. And that's a core attribute of our profession. But we are a field in transition, which is a growing concern. And I'd be remiss not to raise the question, do we have a clear pathway to ensure our profession reaps the higher valuations automation is sure to offer, particularly as we think about infrastructure services and making that a mainstay of our professional identity? Also, domain encroachment is something we must thoughtfully consider. We are a profession that's very proud of collaboration. We see tremendous value in collaboration, but at the same time, we don't want to cede leadership through collaboration or not even being collaborative and just allowing leadership to dissipate based on others seizing opportunity that we're not seizing on. And the last question that to me as an academic is one that really is close to my heart and something that I'm very concerned about. Are we losing ground in recruiting highly talented students? If we do not begin to market ourselves professionally as the leaders in the space, I do worry that very bright and very talented students from a diversity of backgrounds are going to migrate to other professions and overlook our profession because of misconceptions about it being old-fashioned or not high-tech, which is absolutely incorrect given the type of technology endeavors we have today. Also, I think the private investment opportunities that financing brings is absolutely exciting. They can be used to accelerate the renewal of our infrastructure and the deployment of net zero infrastructure going forward. But there are moral hazards as a profession that we're going to have to navigate. And our society looks to us as a profession to really help it navigate some of those tough questions ahead. So with that, I'd like to again say thank you to the leadership of the Center for providing this year's distinguished lecture. For those that are interested in both our strategic vision here at Michigan or some of the work we're doing in our Center for Smart Infrastructure Finance, I provide links there to those documents. So once again, thank you, and I'm happy to answer any questions that the audience may have. Thank you.